Great to see you here. We're starting with another part in the fourth chapter. We're still talking about number theory and cryptography, and now we are looking into solving congruences. Now, when we look at the congruences, it's very important in number theory and in computer science to be able to solve congruences. The first thing that we can consider is what we call a linear congruence. And a linear congruence is a congruence of the form AX is congruent B modulus M, where we try to find all the values of X that comply with this equation. So basically X is the variable, and we know that M divides B minus AX. So we have to find those elements. Now, what we have to find is like solving a linear equation like we did before in calculus and linear algebra. So when we are looking at the equations ax plus by is c, this is in fact in number theory the equivalent element. Now, the principle here is based on what we call finding an inverse of a modulo m. And an inverse of modulo m, we will define how we will find it. And once we have that inverse, we can in fact find the value or the values for x. We also have what we call simultaneous linear congruences, modulo pairwise relatively prime moduli. It will be in fact like a system of linear congruences, and we can resolve them using what we call the Chinese remainder theorem. The Chinese remainder theorem is a theorem that already dates from long time ago in the past, when the Chinese were already looking into congruences and trying to resolve them. Based on that, the Chinese remainder theorem was in fact constructed. There is also what we call Fermat's little theorem, which is also important, and we can use it later to create what we call pseudo-primes. And the last element in this series of videos is what we will call discrete logarithms and primitive roots. We will talk about it in the following sessions. Now, what we're going to do here is, first of all, look into what we call the linear congruence. I already said that the linear congruence is a congruence of the form AX is congruent B modulus M. It's a linear congruence where A and B are integers, M is a positive integer, and X is a variable. Solving linear congruences means that we must find all the possible values of X for which this congruence is valid. There is one, but since we are working in modular mathematics or arithmetics, we have multiple solutions which are possible once we find X. One possible solution, or one way to find the solution for the linear congruence, is in fact to find the inverse A bar of A modulus M, for which the product of A, the inverse of A with A, is congruent with 1 modulus M. So basically we are going to use this in the form of a theorem, and the theorem states that when we consider A and M being relatively prime integers, M is larger than 1, then there is an inverse of A modulus M and its unique modulo M. This means that there is a unique positive integer, the inverse of A bar, smaller than M, that is the inverse of A modulus M, and every other inverse of A modulus M is congruent to the inverse of A modulus M. So basically this is the theorem that we're going to use, and we're going to prove this theorem in different steps. Based on the definition of relatively integer primes, we can write that the greatest common divisor of A and M is equal to 1. So it means that A and M are pairwise relative primes. This also results in the fact that we can express the GCD as a linear combination of A and M with as coefficients the Bezout coefficients S and T that we did before. So basically we can say that S times A plus T times M is equal to 1. This also implies that SA plus Tm is congruent 1 modulus M with Tm congruent to 0 modulus M. So basically we can say that SA is in fact congruent with 1 modulus M, and then we can say that S is the inverse of A bar. So basically based on this element, we can find that, or we can define how to find the inverse of A. And that's also the proof of the theory. Now, when we look at an application on small numbers, it's very easy to find the inverse of A modulus M when A and M are small. We just look for a multiple that exceeds a multiple of M by 1. So when we have that difference that we have 1 larger than M, so we find in fact the inverse. Let us start by finding the inverse of 5 modulo 9. Now we must find a multiple of 5 that is 1 more than a multiple of 9. Now what we can say when we have the congruence, we can say that 9 divides A bar, inverse of A, times 5 minus 1. And when we look at the values, we can immediately see that this is valid for the inverse of A equal to B to 2. Now we can also apply the Bezout coefficients, and since the GCD is of 5 and 9 is 1, they're pairwise relatively prime, we can also write that 9 is 2 times 5 minus 1, which leads to 1 is 2 times 5 plus minus 1 times 9. So now we have the Bezout coefficients for this expression, and we can conclude that 2 is an inverse of 5 modulo 9. So basically we have the two ways to do it. We could find that value looking at the definition of the congruence, and the other element is using the Bezout coefficients. So both elements are in fact, or both ways are practically applicable. Now, when we look at a more efficient algorithm, we can say, first of all, we have to look at the greatest common divisor of A and M. First of all, is this divisor equal to 1? We saw this in the previous slide. We can use the method with the Bezout coefficients to find the inverse. So based on the property that the greatest common divisor of A and M is equal to 1, we can reverse the steps of the Euclidean algorithm to find the inverse. So let's find the inverse of 103 modulo 5310, and is the GCD of 103 and 5310 equal to 1. We can write that 5303 is 51 times 103 plus 57. Now we can say that 103 is 1 times 57 plus 46. We continue, 57 is 1 times 46 plus 11. We continue further, 46 is 4 times 11 plus 2. And 11 is 5 times 2 plus 1. And finally we say 2 is 2 times 1, which means that the greatest common divisor of 103 and 5310 is equal to 1, which means they're pairwise relatively prime, and that's what we wanted to verify first. So the first step is, okay, we find that the GCD of those two numbers is equal to 1. Now what we're going to do is to find the Bezout coefficients. Now we can do the backward pass, and when you have written down the elements, you can find it quite easily, because the first equation said that 11 is 5 times 2 plus 1. So I can write this all as a function of 1, and I can say 1 is minus 5 times 2 plus 11. Now in the equations, we're going to replace 2. So we're going to the equations we had before, and now we replace 2 by minus 4 times 11 plus 46. So that's based on the expressions we find before. So we find this element plus 11. So we have still the same expression. We just replaced 2 by its expression. And we find here that 1 is equal to 21 times 11 minus 5 times 46. So now we continue with the next step, and we're going to 11. We're going to change 11. So basically we find 11 here, and we replace 11 by the expression we found on the previous slide. And 11 is equal to minus 1 times 46 plus 57. So we complete the calculation here. So we have minus 21 times 46 minus 5 times 46, which gives us minus 26 times 46. And I add 21 times 57. The next step is the next number, which is 46. So now we continue with 46. We replace 46 by the value we found before, which is minus 1 times 57 plus 1 times 103 plus 21 times 57. So we just replaced 46 by the other value. Now we find here 26 times 57 minus 26 times 103 plus 21 times 57. So when we have the parameters with 57 together, we find the 26 plus the 21 is 47, which gives us 47 times 57 minus 26 times 103. The next one is 57, so we put 57 in here again, and we find or replace 57 by minus 51 times 103 plus 1 times 5,310. And of course, we still have the minus 26 times 103. Then we add the numbers. So we find here the 103 is 47 times 51 minus 47 times 51 plus the 1 times 5,310 times 47 gives us, in fact, 47 times 5,310 minus 2,423 times 103. And we continue again. Now we have 47 and the minus 2,423. So, in fact, this leads to the conclusion that minus 2,423 is an inverse of 103 modulus 5,310. And we find that minus 2,423 times 103 is congruent 1 modulus 5,310, or that 5,310 divides 2,887 times 103 minus 1. And basically, this was what we wanted to do in this session. So in the next session, we will discuss the Chinese remainder theorem and continue with applications related to this theorem. This was an interesting session, I hope. I think it's a little bit more complicated with all the calculations, and it's very important to do the steps properly, otherwise you may end up with some wrong result. Anyway, you're doing a great job, and I'm looking forward to seeing you in the next presentation. Thank you, and bye-bye.